Okay, so today I'll start with simple trigonometric functions that are sine and cos. So let's first start with sine or sine theta. What is sine theta? Let's say we have an angle, an acute angle theta. Then how do we define sine theta? We draw a normal from this point so that we can make a right angled triangle. Let's say this length is L, the base is B, and in a right angled triangle we have the hypotenuse, the largest side of the triangle, as H. Then sine theta is simply defined as the length or the height that is opposite to the angle L over the hypotenuse H. Okay. Now for this angle theta, which is an acute angle, you can sense that in any triangle basically the length L has to be smaller than capital H in a right angle triangle. So this thing sine theta is less than 1, right? Because small l is less than capital H. Now what happens if we reduce the angle theta? Let's say we reduce the angle theta keeping the hypotenuse or capital H the same. Then this is my new theta in blue. Now we draw another perpendicular. You can see that capital H is kept the same, but now my L has reduced. So if theta reduces, if theta goes down, sine theta also goes down because L is reduced. And in a limiting case, when theta tends to 0, this blue line and the red line will be on top of each other, or this small l will be 0. In that case, if theta is 0, sin theta also becomes 0 because L is 0. Easy? Now let's do the opposite case when theta is increasing. Let's say my theta has increased in a way, sorry about the drawing, that H is kept the same. Capital H is kept the same. In that case, how has the L changed? The L, the normal line, L has increased. Okay, but still the value of L is smaller than capital H. So the value of sine theta for the green triangle is still less than 1, but it's more than the case for this red triangle because L has increased. So if we increase theta, sine theta also increases. But does it increase forever? If we keep increasing theta, does sine theta keep increasing? The answer is no. There's a limiting case again. Let's say, let's use the black one. My theta is approaching 90 degrees. It's very close to 90 degrees. Like 88 degree or something. Okay. So we are having a very skinny triangle where you see that the H will be almost the same as the L because these two are coming to close to together. So L will be almost the same as H, and if theta is 90 degrees, then they are basically the same line. So H is equal to L. So if theta is 90 degree, then L becomes H in a limiting case, and sine theta, which is L over H, becomes 1. So that's why sine 90 degree is 1, sine 0 when the blue line comes on top of the red line. That is the case when sine theta or sine 0, when theta is 0, is 0. Okay. Now what happens if we increase theta further? So at 90 degrees sine theta is 1. If we increase theta further, we go and make an obtuse angle like this. Let's say 100 degree, 110 degree. Keeping the H the same, the hypotenuse the same, we again drop a perpendicular. Okay. Now again, so this length H is kept the same, but now this length L has again reduced. It has reduced. So here when theta was 90 degree, L was equal to capital H, but now The moment theta has gone further up, L has reduced. So now sin theta is again less than 1. So sin theta is maximum when theta is 90 degree, sin theta is 0 when theta is 0 degree, flat line, and then as you increase it further, sin theta reduces again. So if you keep increasing theta further, you encounter the same story, that this thing, the L, the height or the directly opposite to the angle, the side of the triangle, it reduces. So you end up getting smaller and smaller sin theta. So the same story happens if theta decreases from 90 to 0 or theta increases from 90 to 180. So there is a symmetry about theta equals 90 degree. Okay, so keeping that in mind, if we plot sin theta with theta, let's say this is my 0 degree, 90 degree, 180 degree, like that, minus 90 degree, minus, come on, minus 90 degree, minus 180 degree, and so on. So we know that at 0, let's use another pen. We know that at 0, sin theta is 0. When it's 90, this is the y-axis, this is sin theta, this is theta. So when theta is 0, my sin theta is 0. When theta is 90, sin theta is 1. Let's say this value is 1. So these are the points. When theta is 180, that is, we make a half revolution, go all the way here, sin theta is again 0. So you see, it first increases at 90, then after that it reduces again. So you can do this exercise and find the value, draw a triangle. You can actually sit down with a compass and a ruler and calculate the value of sin theta for different angles if you want. But if you do that, you will end up getting a nice curve like this. And if you go the other way around, that is minus, you will see this kind of a behavior. And this thing will keep continuing because you can go 180, then 360, it will be periodic, it will go round and round again. Same thing will happen here, like that. It will keep happening. So that is the curve of sin theta. So this is going to be 270 degrees, this is going to be 360 degrees, this is going to be 540 degrees, this is going to be 720 degrees, like that. You don't have to remember about first quadrant, second quadrant, second quadrant theta is positive, sin theta is positive, third quadrant sin theta is negative. No, you don't need to remember any of those things. Just remember how sin theta looks like, the plot. Okay? Cool. We'll do cos theta now.